Which is, by the way, also why I have added Sam with his permission to the list of authors, because this is mostly work I am currently and in the past have done with Sam. I come at things from a very template and anchors direction, and thanks to Maziar and Andrei Seyfarth, there's this lovely book where we had the opportunity to contribute some chapters that explain why I think templates and anchors are a good perspective, and in particular, why thinking about locomotion as an oscillator is the most basic type of template that we can think about. And so a lot of the work I've been doing over the past decade has been trying to make oscillator theory more solidly relevant to the sort of hybrid oscillators we have in legged locomotion. And so primarily these two papers, the first of which showed that if you have isolated transitions on a limit cycle, you can sort of smooth those out, and really nothing new happens in this class of hybrid systems compared to smooth systems. And then the second paper, which is the cause for most of what I'll talk about today, deals with the case when you have multiple legs hitting the ground at the same time. You have this intersection of hybrid guards. That was actually not really handled in the literature, except in very, very abstract ways by Filipov before the work that Sam and I did. And in particular, what I'm talking about today is about this. So as you see from this cockroach, this is what happens in your house at night when you're not watching. These guys walk around. Yeah?
Sorry, if you could just go back one slide. I don't understand some of the words you're using, like hybrid guards. What does that mean?
So the guard in a hybrid system is the surface upon which the dynamics switch between smooth modes. So in the context of legged locomotion, that's usually the touchdown event of the leg. That's a surface in your state space where the dynamics are changing discontinuously. And the problem is when you have two legs that might hit the ground at the same time, you're crossing through the intersection of two surfaces. That makes for some very weird indeterminacies of which order of events, just like the talk we heard before about collisions and the complexity of which order events might happen. So this talk is about an alternative approach for analyzing what happens in those cases. So what Sam and I showed in that paper, one of our theorems shows that this class of systems that appears in multi-legged locomotion and grasping and a bunch of other places has a special kind of derivative, which is not the conventional derivative we learned in our calculus classes, that governs the first order perturbation. It's called a B derivative or a Boulegan differential. And so the general goal that we're trying to achieve, that I'm going to talk about in this talk, is really how do we analyze stability or do optimization on a trajectory, which usually means we want to do perturbations off of that trajectory and see how they evolve in time. Now in smooth systems, the way that happens, if you think about just this red trajectory in one smooth domain, we have a linear time-varying equation along that trajectory, which lets us know how small perturbations off the trajectory in the beginning end up being some other small perturbations off the trajectory at the end. And sometimes if things are bad, those won't be small perturbations, and we know that this trajectory is pretty sensitive to initial conditions. And other times, it's really stable, and we can be pretty lax about how we move along that trajectory. The other thing that's been known for a long time is if we have a guard, like say this blue guard, and then a new smooth trajectory on the other side, well, what you do is you do a linear time varying system until you hit the guard. Then at this point you apply a matrix that can be computed in a straightforward way, and then you do another linear time varying system on the other side. So all of that's been known literally for centuries. The new ideas that we had in our paper is what happens when you have a second guard that intersects that. Now the thing you need to add here in the middle is no longer a matrix, it's this B derivative jump. And the question is, how do you represent that computationally, and how do you compute that efficiently? And oh, by the way, if you compute that efficiently, you also get a really fast way to compute which contact sequence will correspond to each set of perturbations off your trajectory. So you know that, oh, if I jiggle slightly left, then this leg will hit first, this one will be second, and this one will be third. I always say I as or B as a cockroach, because that's what I think. So the general picture is, in our original description, we have something like this. We have some surfaces on which there are non-smooth transitions, and we're flowing through them. Leg 1 hits and then leg 2, or maybe leg 2 and then leg 1. But we can do a change of coordinates and make these surfaces flat. And that's the first step. And then if those surfaces are flat, what we care about around the multiple transitions is right here in the middle. And if we zoom in really tightly in here, all these changing smooth arrows become constant, and we really are looking at a system like this. And in our paper, this is called the corner flow, because it's the flow that happens in the corner, where the corners of these domains meet. And so the question is how to compute the derivative there. And here's the naive approach. Here's the naive approach. If there are m surfaces, there are m factorial orderings in which these surfaces might be crossed. Bad news for everyone, all m factorial will always appear. We can prove that. So it's going to be pretty bad if you have 6 legs. It's going to be 6 factorial. And for each contact sequence that I can walk through, well, if I want to compute the Jacobian of a flow going through here, if I went along this trajectory, and my dimension is d, I need d plus 1 trajectories to be integrated. So in general, it's going to be something along m factorial times d plus 1 integrations of my system to know what the results will be for every possible contact sequence. And if I'm smart about caching these results, I can figure out which contact sequence I have, and for the rest of the queries I might run, I can just keep the data I remember. Now each integration here is a regular integration of an ODE. So depending on my time step, delta t, there might be a lot of operations I need to do, each of which is on the order of the dimension. So just to give you a sense how much work needs to be done. We need to do a factorial number of contact sequences and then d plus 1 integrations in each of them. What our algorithm does is we've figured out that there are 2 to the m points that you can pick that are very special. And what's special about them is that they exactly partition the space into each of the possible contact sequences. They can be computed in a straightforward way. Now, if there are additional directions in the space along which there are no transitions, and that's usually the case, usually we have only a few transitions in a larger state space, in those directions you only need a smaller number of points. And then we integrate just those points, but the other thing is we can integrate them through the corner flow, which is nice and straight. So because these are constant vector fields, this integration is super fast. Notice there is no delta t in here. The number of steps here depends only on the dimension. So this integration gives you the contact sequence hundreds of times faster than running an ODE integrator. And so combined together, what we get is a super exponential improvement. We went from m factorial times d to 2 to the m plus d in terms of speed up. So if you have lots of potential contacts, this is a huge improvement. Even for a moderate number of contacts, 4 or 5 contacts, you feel a pretty big improvement. And the other thing is the fast contact sequence calculation gives you a great advantage as well. Now, I won't describe the details of any of this more, but just so we show you some animations that kind of visualize this. So here, we took 3 intersecting surfaces, 3 intersecting events, like what would happen in my favorite cockroaches, and we can pick these specific points, and if you look carefully, you'll realize that the points we pick do something very unique. The trajectories starting there go through the intersection of 2 surfaces, and then through 1 surface, or the other way around, through 1 surface and then the intersection of 2 surfaces. And so these are very, very special points, and thanks to knowing the trajectories of these points, I know that the pyramid in red gets transformed into the pyramid in blue. And because it's a pyramid, it's 4 points in 3-dimensional space, it completely determines the Jacobian for that piece of the space. So by picking these very special points, it becomes straightforward to solve for the derivative in all the domains with far fewer integrations. And as a second illustration, if there is a direction, in this case z, in which there are no transitions, I have triangles because there are only 2-dimensional things for the transitions, and another perpendicular direction to account for what happens in z. And this is enough to figure out all the pieces that will occur here. We validated this on a case that has a closed form solution where we know exactly what each of these derivative pieces are. This is the exact calculated derivative represented visually. This is what we get from our estimate. We can't tell the difference. That's pretty much down to numerical precision. And then we did a slightly more interesting physical example. This is a bouncing chair. So it's a chair with two springy legs. It falls on the ground. And if it falls with exactly both legs hitting at the same time, it's going to have potentially a different sensitivity if the left leg hits first versus the right leg hits first. We need to partition the space the right way. So in general here there are two transitions. It's a 6-dimensional state space because we have 3 degrees of freedom and their associated velocity. For a single trajectory, we're 200 times faster than doing a regular ODE integration. And for computing the entire object we want to compute, we're 400 times faster than doing that computation naively. And this is a measure of the accuracy, just to say we get pretty good accuracy in recovering this object. So what am I trying to tell you? I'm trying to tell you that if you have a problem where you have multiple contact occurring and you want to be able to understand, is this going to be a bad thing or a good thing? Are these multiple contacts going to stabilize me or throw me completely off balance? And if this was a smooth system, you'd know what to do. There's a textbook answer that's been around for hundreds of years. Well, we have an algorithm that can do this through the multiple contacts now and do it pretty efficiently. And yeah, that's pretty much all I had to say. If you're interested about the other parts of the things I have in the talk, I have those slides. Talk to me after. Thank you.
All the things that you showed, the discontinuity was discontinuity in the flow at the boundary.
Yes.
But early in the talk, you said that there's actually a jump, you could reduce that to a continuous system. You said if there's actually like the collisions you show are collisions of mass changing the differential equations, but not a jump in state.
That's true.
But you said if you put a jump in state, you can make it smooth again by changing variables. Is that correct?
No, if that's what came across, that's not what I meant to express.
But so, but in the examples you showed, there was no jump in state at the boundary.
That is true, there's no jump in state. For a broad class of jumps in state, you can do a surgery on the space and reconnect it so that, formally speaking, you have no jump in state, and then this can be applied.
That's not what you were talking about, though.
No, that's not what I'm
So
talking
you don't, if there is a jump in state, I just think if the collisions we're having are massive collisions, so there's a jump in state, so massive collisions like the one you showed, I don't think this idea works. Like,
Well,
I don't think that surgery that you're talking about works in that case.
Well, we should maybe discuss that offline, but certainly more work is required. I'm not claiming that when you have collisions, plastic collisions with mass, this will provide a solution. This is why we went with massless springy legs in our example.
I had a quick question.
Yeah.
Can you intuitively explain how you got rid of the integration?
Yes, so the intuitive explanation for how we got rid of the integration is really packed into this. So if your vector fields are piecewise constant, then if I wanted to know where this initial condition exits, I can just compute that directly from the coordinates of this vector in one step, so I know immediately that I go here in one computational step. So I don't need to actually integrate through the space. Because
so
we
is it
can
kind
read
of a small space assumption, or you're assuming that it's constant?
Well, the local behavior of the system is provably dependent only on these constant vectors. So that's why we can do it.